Hello, everyone. This is Hans Taylor. I'm a second year master's student working with Dr. Marcus Putters, studying cloud microphysics and, in particular, ice nucleation. This presentation will revolve around the need to understand the role that primary ice formation has on precipitation. The research that will be presented in this talk addresses this need in two sequential components. The first was a serendipitous discovery of a need to improve apparamerization within a microphysical scheme. The second is assessing the influence that ice nucleating particles have, or INP, on precipitation. Before we get into all that, I'd like to first present you with my initial hypothesis for my research. In doing so, to give you a bit of background on why it is I care so much about ice nucleating particles, ice crystals, and why I really think they're worth investigating. So my hypothesis appears quite simple. Precipitation increases with an increase in the ice nucleating particle concentration, or INP, available in the atmosphere. And that's illustrated off to the left here as we go along the x-axis from a maritime air mass, or very low INP, to a continental air mass, or higher INP. We see an increase in the total precipitation over the domain along the y-axis. The reasoning behind this hypothesis is that as we make available more ice crystals in the atmosphere, we're cranking up the knob on the vapor depositional growth process, also known as the Wegener-Burgeon-Venn diason process, which is a process in which ice crystals can increase their mass at the expense of water vapor, or even perhaps liquid water, and that promotes their fallout. Now, there's a caveat in this hypothesis, which is illustrated off to the left as well, is that at a certain point, a further increase in the INP will actually have a negative impact on the precipitation. And if you can think of it like this, if we saturate a cloud with so many ice crystals, at a certain point, the ice crystals are now in competition with one another for water vapor. And this competition for water vapor actually limits their individual growth, thereby inhibiting their fallout. And so now moving forward, the motivation for this work, I think, can be well illustrated by the figure off to the left here by Molenscheit et al. 2015. In it, they suggest that the cold phase processes dominate the precipitation over much of the Earth, especially over the continents, which is indicated by these warmer colors, which indicate a higher fraction of precipitating clouds over a 5-year period that are involving the cold phase, ice processes. So we know that ice nucleating particles have a role in precipitation, but assessing that role in microphysical schemes may lead to more representative models that are more representative of the atmosphere. And in doing so, this also may lead to better performing weather forecasts, especially precipitation forecasts. I couldn't even begin to exhaust the list of implications that come from improving the forecast in this presentation today. The microphysical scheme at the core of this project is the WSM6. That stands for the Whorf Single Moment 6th Class Microphysics Scheme. And its name, like its predecessors WSM3 and WSM5, come from its ability to discern between 6 different varieties or flavors of water, shown here in the schematic by Hong and Lim, 2006. In addition to showing the 6 different varieties, this schematic is also showing the way that they can actually communicate with one another through these various microphysical processes. The 3 that I'm mostly interested are the 3 here circled in red that are relating or involving the cloud ice class. Before I get into those 3 processes, first I'll give you a brief reminder on the various pathways in which we can get ice crystals to form in the atmosphere, using this illustration off to the left by P and L. So the first process on the left column here is of homogeneous freezing. Now this is the simplest in which you can get ice crystals to form because it doesn't require the need for any impurity or ice nucleating particle. However, it does require much cooler temperatures, anywhere between -38 to -40 degrees Celsius, than the heterogeneous pathways. And going forward with this research, I've routinely removed this process from the model to put emphasis on the immersion mode, and the kind of support in doing so comes from the idea that once we get down to -38 or -40 degrees Celsius, the lion's share of ice crystals that are being supplied to the atmosphere would have been supplied by the immersion mode freezing and not the homogeneous freezing. The second process shown in the yellow here is of deposition nucleation. This is where you get water vapor directly depositing onto an ice nucleating particle to form an ice crystal. And similar to the homogeneous process, in this research, this is routinely removed from the model due to the prevailing thought that the deposition mode of ice nucleating particles are very rare relative to the immersion mode, and they really don't contribute the dominating or the majority of the ice in the atmosphere. The last one is of immersion freezing. And this is where you have an isolating particle already immersed within a cloud droplet. And at a certain temperature, that particle becomes activated, allowing that cloud droplet to crystallize. So here it is, this equation down below is of the immersion mode. Went ahead and set off to right here. And the next few steps I'm going to have to go through quite quickly for the sake of time, but I just want to go and show you these just to show you that there's nothing magical in what was done to improve the parameterization of this immersion mode freezing rate equation. So multiplying this equation by 60 seconds, it allows for one to determine how much ice mass would freeze if you held the atmosphere there for 60 seconds at a particular temperature. From that, you can get the number of droplets that are frozen. And from that, you can get the fraction that's frozen. And the fraction that I'm interested in is the 1/1,000,000th. So at what temperature along the x-axis do you get a millionth of the cloud droplets, say, in a cubic meter of air to freeze if you had a cooling rate of 1 Kelvin per minute, which is 60 seconds. And so we're going to head and plot that off to the left here. And just like to note that 1/1,000,000th mark, this is essentially the number of ice nuclei that we would expect to be out in the atmosphere. 1/1,000,000th of the CCN or cloud droplets in the atmosphere would be ice nuclei. And now we're going to crank up the cooling rate. And so cranking up the cooling rate is essentially the same idea as increasing the updraft of the cloud. You can imagine that as you increase the rate at which cloud droplets are ascending within an updraft, you're actually increasing the rate at which these individual cloud droplets are cooling. So going from 0.01 Kelvin per minute, going up to over 4 orders of cooling, up to 10 Kelvin per minute, we get this sensitivity line, and the slope of which in the model is 3.49 degrees Celsius per decade per order of cooling rate. Now the problem with this is that this is not in line with what we observe. The light blue colors are showing the measurements, the sensitivity measurements made by Wright et al. 2013 of precipitation samples that indicate that we should expect a sensitivity between 0 to 0.75 degrees Celsius per decade of cooling. So to bring the model in line with what we observe, or what we should be expecting, I went ahead and created an N ratio of what we expect versus what's in the model, and took the nth power of the time element in this immersion mode freezing rate equation shown down below. So just to recap, I've improved the parameterization of this immersion mode freezing rate equation by adjusting the time dependency of the rate equation. To the second part, the second component of this research is to assess the influence that INP have on precipitation. What I here have shown off to the left is a recently produced composite by Petters and Wright 2015 of isolating particle concentrations within a continental air mass. So you have freezing temperature along the x-axis and the INP concentration per liter of air along the y-axis put in log space. So just note, a decrease in temperature actually leads to an exponential increase in the available INP in the atmosphere. So I went ahead and overlay both lap sea spray and marine boundary layer measurements. And as you expect, with the marine boundary layer being cleaner, more pure, we would expect lower concentrations throughout the temperature spectrum relative to the continental air mass shown in the dashed purple lines. So showing all of this, what we can do now is get 4 cases that we can present to the model that vary over 5 orders of magnitude in the INP concentration. And in doing so, we'll be assessing the influence of the INP on precipitation, going from an ultra-clean maritime air mass shown in the light blue up to a polluted continental air mass shown in the light green. The terminal design that we'll be feeding these models into, or these runs into, the configuration is shown below, with a little bit of eye candy shown above. This is a simulation of the accumulated or integrated water vapor in the atmosphere of an atmospheric river event impacting California. And this made impact from February 5th to February 10th of 2015 during the CalWater 2015 field campaign. This atmospheric river event was picked due to the fact that we have measurements within California along the coast of the INP for both the air and precipitation, so we can use that and plug that into the model as one of our cases. And again, all of that, those cases using that experimental design is to address the hypothesis that precipitation should increase with an increase in the available INP in the atmosphere. Before we get to those results, though, I'd just like to highlight an interesting finding. Going back to the initial assumption that we would be able to remove the heterogeneous deposition nucleation process, because the prevailing thought is that there's not that many deposition mode INP in the atmosphere, and that it shouldn't be a contributing factor of ice crystals in the atmosphere. So this figure here is showing the hour simulation along the x-axis, and on the primary axis on the left is showing the mixing ratios of various constituents in the cloud, going from cloud ice to snow to graupel, with blue being the total of the three below. Along the secondary axis is accumulated precipitation, which is the dashed black line. And so this is a control case with nothing affected in the microphysical scheme. And now we're going to go ahead and remove the heterogeneous deposition nucleation. Case B here. I'm going to go back and forth here. So what we're seeing here, if you can focus in on the orange line shown down below, shutting off the heterogeneous deposition nucleation process, we're actually seeing a reduction of about 30% in the amount of cloud ice in the atmosphere. So this is just an interesting finding that there's clearly this disconnect between what's in the model and what we observe, where what we would expect is that heterogeneous deposition nucleation backed up by observations shouldn't be a contributing factor, but in the model it is. As for the results for precipitation, we found that precipitation was not sensitive to varying the INP concentration over 5 orders of magnitude, which is shown along the x-axis. Going from a maritime air mass on the left, going to a continental mass, we see a negligible impact along the y-axis, which is the cumulative precipitation. So this brings up an interesting finding, though. If we're tweaking or adjusting what is thought to be the dominating source of cloud ice in the atmosphere, that immersion mode freezing rate equation, we can go from by ranging that, by varying that by 5 orders of magnitude from 10 to the negative third, 10 to the second here, ultra clean maritime air mass, to polluted continental air mass. If we don't see any change in the amount of cloud ice in the atmosphere, shown in the orange line here, it would be hard. It's hard for one to expect that if you're not changing the amount of cloud ice in the atmosphere, to expect a change in the accumulated precipitation. So if what's thought to be the dominating source of cloud ice is not actually affecting at all the amount of cloud ice in the atmosphere, what is? So to try and to address that, to figure out what is, went ahead with the 3 equations, the 3 sources of ice in the model in the simulated atmosphere. So this is the control case, and this is removing the 3 sources. And what we find is that there's still plenty of ice in the atmosphere, shown in the orange line here. So we're not removing any ice in the atmosphere. We also don't see, of course, any impact on the accumulated precipitation. So now the question is, or at least what led us to believe, is that if the microphysical scheme isn't providing any, and if that's not providing any ice to the system, but there is ice in the atmosphere, then perhaps CP scheme. So off to the left here is the Kane-Fritz CP scheme that we've coupled it with, and went ahead and reran the same runs using the Betz-Miller-Ionic CP scheme off to the right. These are both the control cases where nothing is removed. And then now showing what happens when we remove those 3 sources of ice. What we're seeing off to the right is that in the Betz-Miller-Ionic, we are removing all the ice in the system, and we do see an impact along the secondary axis on the accumulated precipitation, but not in the Kane-Fritz CP scheme. So this is the finding that the Kane-Fritz CP scheme is indeed feeding ice to the nested domain. So this has its own implications, will be discussed near the end of the presentation, but it's quite interesting to note going forward. As for rerunning all those runs now, coupling it with the Betz-Miller-Ionic, what we find is that the impact shown here in the yellow of removing all sources of ice actually has the same impact of running the model with an ultra-clean maritime air mass and that of a clean maritime air mass. But once we get to a certain INP concentration or a certain threshold shown with the maritime air mass, we do see the cloud physics becoming active and contributing to the accumulated precipitation. We see that bump along the y-axis. But any further increase in the INP concentration going from a continental air mass or a polluted continental air mass, we see no sensitivity, no additional contribution of precipitation. So now this promotes, or this comes up with this idea of an INP threshold. So below 10 to the negative 1 per liter within the atmosphere, ice physics are not active, and we see a reduction of precip by 12.5%. But once we meet that threshold or exceed it, then we see that contribution of ice physics on the accumulated precipitation. This idea of the IMP threshold, in order to really understand it, requires one to really understand the microphysical scheme itself. And part of that is to understand that the cloud ice source terms, these equations that we've been tweaking, especially this immersion mode freezing rate equation, it's not directly contributing to the ice crystal number concentration, or in ice, in the atmosphere. This in ice is actually artificially bounded from 10 to the third to 10 to the sixth per cubic meter. And that's shown to this in the figure off to the left here by Hung et al. 2004 along the y-axis. And that within those artificial bounds, the in ice is actually derived from the cloud ice mass. So going along the x-axis in this illustration off to the left, over 4 orders of magnitude in the amount of mass in the cloud ice were artificially bounded by 1,000 crystals to 1,000,000 crystals per cubic meter. And that's really, to a large degree, independent of temperature. And so what we did previously is that what we find is that once we meet this IMP threshold, we actually were able to provide enough ice to the system, enough ice mass to the system, to promote these runaway secondary ice growth processes such as accretion and deposition. And that's what happened once we met 10 to negative 1 per liter. Any further increase in the IMP concentration, we didn't see any sensitivity to accumulated precipitation because these secondary growth processes took over. So you can't discern any impact from increasing more on the immersion mode freezing rate equation. So as for the summary of findings, as for testing the original hypothesis that precipitation increases with an increase in the IMP, the result, although a bit convoluted, is that yes, an increase in the IMP concentration does lead to an increased precipitation. Once you're able to meet that threshold, you do see an increase in precipitation. But this comes to another finding, that this whole role of the primary ice formation is exclusively dependent on this IMP threshold. If this IMP threshold is not met, then the primary ice formation has no role on precipitation. And once it is met, then it does play a role. And lastly, although we don't really have much time to get into it, it's really important to note that the Kane-Fritz scheme, although this is largely known that it does promote ice and produce ice in the system, the implications of it is something to take note for future studies, that it's providing enough ice in the system to overcome the IMP threshold and make it impossible to discern the importance of the various cold cloud microphysical processes. So this is to note going forward that if one wants to discern the importance of the cold phase microphysical processes, one must not couple it with either Kane-Fritz or even the other CP schemes that actually produce ice in the system. And this is something that probably should be addressed going forward, since the Kane-Fritz and other CP schemes are useful, but if they're providing too much ice where the microphysical process, the cold phase processes, are essentially worthless, useless, they don't contribute. That's something that should be addressed. Lastly, I'd like to acknowledge a few people for this presentation, this research. The first is Dr. Brian Mapes of Miami State University for producing the Mapes IDV plugin, which was used for the analysis of the various cloud mixing ratios, such as cloud ice grapple and so on. And also for the previous research done by Dr. Marcus Petters and Dr. Timothy Wright. And lastly, for the invaluable counsel provided by Dr. Gary Lackman throughout the semester on this research project.